Hi, welcome to another episode of ElectroBOOM 101, where I will teach you electronics by over-editing my video to make it look even more interesting. I have covered a bunch of things so far, watch them if you haven't, because slowly we are getting to a point where we can design stuff together. I have talked about resistors, capacitors, and inductors. Resistance and capacitance deal with electric fields, while inductance deals with magnetic fields. So one can model the entire electromagnetism using these properties. Well, maybe not all of it, but close enough. Resistors resist against the current flow and convert the energy into heat. Ouch! A capacitor stores energy in form of electric fields between electric charges and can later release them when a load is connected between... Damn it! And if you don't know how to use them, it will convert the energy into heat. Inductors store energy in the form of magnetic fields. Oh sh**. And yeah, I guess every wire has a resistance too. Any other components in electronics like transistors, diodes, antennas, or transformers make use of and manipulate these three properties one way or another. Now let's try to learn how to analyze the circuit, and for that you must understand what a lumped model of a component is. Let me read you a passage from my electronic Bible. Lumped model. What is lumped model? Eventually shall perish those who don't use lumped model. Well, basically the lumped model of electrical elements significantly simplifies the life of us primitive engineers who would have to analyze complex circuits quickly. Otherwise, you would have to resort to complex equations, science, and computing, which you can learn very easily using my sponsor, Brilliant. There, you can learn tough concepts very easily using interactive courses and problem-solving quizzes to make it stick in your brain. So go to brilliant.org/electroboom, where the first 200 viewers get 20% off and start learning like never before. But what is a lumped model? Have you ever been so sad that you felt like a lump was appearing in your throat? You could scream and cry, but because you're a caveman, you bottle up your feelings and take them to your grave with you where they belong and act like everything's fine. Lumped model is the same. Basically, in a lumped element model, all sort of radiations from magnetic, electric, or even heat are bottled up inside the component and don't leak out. Only the voltage and current are affected by the component. This makes life very easy, because if components don't bottle up their and radiate stuff around, they start affecting the surrounding circuits, and this crosstalk between the components makes it very hard to analyze circuit behavior. For example, if a hot resistor gets close and warms up a transistor, the transistor parameters are significantly affected. If an inductor radiates magnetic fields, it will induce unwanted current in the neighboring circuit loops. If electric fields leak from a capacitor, they can create unwanted voltage on neighboring conductors. And all these leakages make it very hard to understand the circuit behavior. Everything is lumped. No one is affecting anyone else. But the fact is, no component is truly lumped. All components always radiate and affect each other. But hey, we are not here to deal with black magic, so nothing will affect nothing. At least for now, until we grow a little bit more. And with that, let's jump into two of the most important laws of electronics, first described by Gustav Kirchhoff. Kirchhoff, yeah, called Kirchhoff's circuit laws. One is Kirchhoff voltage law, or KVL, and the other one is Kirchhoff current law, or KCL. You need to understand these well, because soon we will be designing circuits together. These laws are easiest to understand and work best when the components are lumped and nothing radiates on nothing else. So let's start from there. Kirchhoff voltage law states that in any closed loop of a circuit, the sum of all voltages across components in that loop is zero, and that's based on the law of conservation of energy. And lumped model makes it easy. I'll talk about that later. According to my definition, KVL is not this. Let's expand it a bit. Imagine we have a circuit like this, and I don't know the polarity of voltages across components, but I want to know their relations. First, I assign polarities across the components any way I like. One important thing you should remember is that it doesn't matter how you assign your polarities as long as you stick with them forever. You can't change them halfway or you'll have to start over. For example, if you assign your voltage like this, but the actual voltage is positive this way, it doesn't matter. The value you get for your voltage assignment will be negative, which is absolutely fine, so don't worry about it. Now let's play a game of how many loops you see in the circuit. 4, you say? Wrong! There is only 3 loops. One is this big one is this small one, and the other one is this one. Now we have to start adding voltages in loops along one direction in a loop. It doesn't matter which direction you move through the loop. It can be clockwise or counterclockwise. But for fun, let's keep them all clockwise. Now moving through a loop, if you enter the positive terminal of a component, write a positive voltage for it. And if you enter a negative terminal, write a negative voltage for it. Like here, we enter negative V1 minus V2 plus V3 is equal 0. And make sure you write all the voltages in that loop. In the next one we have minus V3 minus V4 minus V5 is 0. And in the big loop we have minus V1 minus V2 minus V4 minus V5 is 0. And of course if you move the other way in the loop, all these voltages will be positive, which is the same thing. And you have 3 equations just like that. Of course, these are not unique, and from any 2 of them you can get the third one. Because for example here, 2 small loops make 1 big loop. So 2 of them are enough, and always go with the smallest one for ease. Or for example, if you have a circuit like this and write KVL for the first one, you have minus V1 plus V2 is equal 0, or V1 is equal V2. Similarly, in the second one, V2 is equal to V3, which means V1 is equal to V2 is equal to V3. This is fantastic. It means that the voltage across all parallel components is always equal. Remember this. So that's what you get from KVL. But those equations are often not enough to solve the voltage and current values. And that's when you need KCL. According to KCL, if you have a bunch of circuit branches connecting in one node, the sum of all currents going into the node is equal to the sum of all currents going out. Otherwise, it would mean the charges are accumulating in the node, which is impossible. Minding the lumped model again. Stay tuned for more clarification. It makes sense, doesn't it? It is like if there is no leakage current, then all the water that goes into a pipe must go out of the other side. Otherwise, the pipe could bulge and explode. And as we have defined, the current is positive in the direction of the arrows. Again, it doesn't matter if you know the actual direction of the current. You can assign them randomly. For all I care, all these can point into the node, which would just mean that some of these currents would have negative values, or the sum of all these currents would be 0. So based on KCL, if you have nodes with only 2 components connecting to it, which means they are in series, I1 going into the node is equal to I2 leaving the node. Or here, the same, I2 going in is equal to I3 leaving. This is fantastic too. This means the current through all series components is always the same. Remember this too. Let's look at this circuit. It has 4 nodes, 1, 2, 3, and 4. But 2 of these nodes don't matter because they put components in series, and we already know the current through all of them is equal. So only these 2 nodes are important for our analysis. So in this node, I1 going into the node is equal to I2 plus I3 leaving the node. And in this node, I2 plus I3 going into the node is equal to I1 leaving the node, which is the same as the first one and is not unique. So here we only have one useful equation, and that's what KCL does for you. Yeah, you can assign polarities and directions randomly, but it helps understand the circuit better if you assign them properly. For example, start with your power supply. If you already know the polarity, put it on. Otherwise, for example, if it is AC, put positive on the top side. Then the direction of the current goes out of the positive of the power supply and distributes through the load and splits in branches and returns to the supply. And on the load side, the current enters the positive terminal of the load. So you can easily put polarities there. This kind of assignment keeps your values positive for DC, not so much for AC, but using it will give you a better understanding of the flow of your circuit. Very simple. Now you know lumped model, KVL and KCL. Let's do an example. We have a circuit like this with an 8-volt power supply and a bunch of resistor values like this, and I've assigned polarities and directions as you see. Writing the KVL and KCL equation, we see in loop 1 we get this equation, in loop 2 we get this equation, and in this node we get that equation. 7 variables and 3 equations. Not enough. But we already know the relation of voltage and current in resistors, where if the current enters a positive terminal of a resistor, voltage across the resistor is resistance times current. And just like that, we get 4 more equations. Now we just have to sit down and solve it. What? Your math requires improvement? Go to Brilliant and start learning math. Click on the link. Now don't be intimidated by such a simple, stupid circuit. All you need is a little bit more information to be able to solve it even easier. For example, I know these two are in series, so their equivalent resistance is 1 plus 3 or 4 ohms. And this 4 ohm is parallel to that 4 ohm, so the equivalent resistance here is 2 ohm. And that 2 ohm is series with this one, so the equivalent resistance here is 4 ohms. So this entire circuit is like an 8-volt supply across a 4 ohm resistor. The current going out of the supply is 8 volt divided by 4 ohms or 2 amps. As soon as we know I1, V1 is 2 ohm times I1 or 4 volts. Right there from KVL in this loop, we know V2 is equal 8 minus V1 or 4 volts. And easy as that, we know I2 is V2 divided by 4 or 1 amp. And from KCL, we know, I leave the rest to you. That first bit about equivalent circuits was important. I should just tell you how series and parallel stuff work. But I won't, because we already have much information to digest. I will make a video later about equivalent circuits, and that will help you simplify the circuits for analysis. But for now, KVL and KCL are enough as long as you have lumped model elements. But what if you don't? What if the stupid elements are real and leak radiations around? Some people even argue KVL and KCL don't hold in such cases. No, let me put your mind at ease. KVL and KCL always hold true as long as you have your definitions straight. But they only give you results as accurate as your model, so you have to know every single element that's affecting your circuit. For example, imagine I have a loop like this, an AC supply across a resistor. I measure the voltage across the resistor and it doesn't match the supply voltage. What the hell? The reason might be another inductor radiating magnetic fields through my loop creating voltage. So I must understand there is a missing element in my model that I didn't consider, and that's the loop inductance acting as a secondary of a transformer. I put it in and the KVL holds, like I battled it out in one of my old videos. And imagine you have AC current going into a node and going out of the other side, and you expect both to be equal. You measure and they're not. This means there must be a third current leaking out somewhere. But where? Maybe your wire is running too close to ground, and that creates a stray parasitic capacitance between your node and ground that you didn't account for and is sucking the current away. So as long as your model is accurate, KVL and KCL are accurate. And all this nasty shit happens in AC, where you have most radiation. In DC you only have to worry about heat, and that's pretty much DC. It changes so slow. Now sometimes these stray parasitic components are so many you ignore the ones with negligible effect and only include the ones with the largest effect in your model. Which is fine. In electronics or any engineering, we define an acceptable inaccuracy for our application and design our circuits to work with that tolerance. So don't worry about things so much. We will design simple stuff together soon. It requires very simple math, but if you're worried about your math level, go straight to brilliant.org/electroboom. There you can take mathematical fundamentals. These look quite fun. Brilliant is filled with very well-made courses on math, science, and computing, from basic algebra to quantum computing. But most importantly, they made it super fun to learn with their interactive platform. Are they me? No, I'm not interactive. Did you know that you can also click here and give the Brilliant membership and the treasure of knowledge to someone else?
Do it now!
So go to my link and sign up for free, and you'll have access to tons of free stuff already. But the first 200 people to use my link will get 20% off of the annual premium membership for full access. And you could call yourselves big brain too. And thanks for watching.